Here's a generic problem with a pump. Typically we might start with a reservoir down here, pipe running to a centrifugal pump, through a piping system with some bends and some valves and things, to a vessel up here, which might be a closed vessel at some pressure. So we'll write Bernoulli's equation from location 1 to location 2. Z1 plus P1 over rho g plus V1 squared over 2g plus whatever energy we put in with the pump, so delta HP, must be equal to Z2 plus P2 over rho g plus V2 squared over 2g plus whatever energy we lost to friction and to minor losses. So this is an energy balance. The energy that we had at location 1 plus any energy we added in this pump, we must still have at location 2 unless we lost it along the way to friction or minor losses. So if we rearrange that, we wind up with delta H for the pump must be equal to delta Z plus delta P over rho g, so the elevation difference and the pressure difference, plus V2 squared minus V1 squared over 2g, plus FL over D, V squared over 2g, plus sigma K, V squared over 2g. Now keep in mind that the V squared over 2g in this term, the loss terms, is the velocity in the pipe, not the velocity necessarily at location 1 or location 2. So typically this depends on the pipe, depends on the velocity in the pipe and the details of the piping. V2 and V1 certainly in this case and very often are completely negligible. Usually this is specified, the pressure difference. We'll know what the pressure is inside the vessel and how that differs from the pressure out here, which in this instance looks like atmospheric. Likewise, from the problem specification, we should know how much elevation difference we've got here. This is how high up the mountain we're trying to get things. And we also know the head rise across the pump, depending on what the particular pump is. So that actually turns this into an over-specified problem to some extent. But let's see where we go with this. So for the minor losses, we need to look at the minor loss coefficients. Let's assume we've got a rounded entry, so K is about 0.2. We've got an exit up here. That's always going to have a K factor of 1. 3 elbows, taking values from the table in Munson, so 3 times 0.3. 2 ball valves, 2 times 0.05. Really smooth inside on a ball valve, almost no resistance at all. And a globe valve, which in Munson it says has a value of about 10. Sum all of those up, and the total's 12.2. And most of that is this globe valve right here. So we've got two problems we can look at. One is, what's the minimum pump to provide the flow that we want? In that case, we'd have a specified flow rate. We know Q. We know what the piping looks like. We know what delta P is, the pressure difference. That is the pressure inside the vessel. And we know what the elevation is. So we've got the whole system. We just want to know what will it take for our pump to be able to drive that. So that'll tell us what the head rise has to be across the pump from this equation. So we don't know which pump we're looking at yet. It'll tell us how much the head rise has to be and what flow rate we have to be able to get that head rise at. And that'll tell us which pump we want to buy. The next question is, after we've decided on which pump we want to buy, or which pump we already have, and the piping we already have, what happens if we turn it on and measure the results? And the flow rate will depend on the interaction between the pump and the piping system. And we may have cavitation problems, and I'll talk about that in a moment. So we've got three things here. We've got delta Z. So no matter what the flow rate, Q, for any value of Q, any value of flow in that pipe, To make it go forward, we've still got to have a head rise across the pump that's bigger than the elevation difference. So the elevation difference factors in all the time. We still have to have a head rise that overcomes the pressure difference. If we're pushing against a pressure gradient, we have to overcome that pressure difference all the time, no matter how much flow we're trying to move. If we get the elevation difference and the pressure difference and just a little bit more, then a little bit of flow will start to move between here and here, forward through the pump. Just a little bit. If we want to have more flow going through, then we're going to have to overcome the system friction as well. And the more flow we have, the more friction we have. It goes up as the velocity in the pipe squared. So this region under here represents FL over D plus sigma K times V squared over 2G. As the flow rate increases, the velocity increases proportional to the flow rate, and V squared over 2G goes up parabolically. So this curve here is what the system needs in terms of how much head has to be delivered by the pump to get that much flow to go through it. We need to compare that to what the pump can do. This line here we might have as a typical pump curve of what the pump can do. So if we turn on this pump and we have no flow, we'll see a head rise across the pump that's quite large. And typically it'll peak about here and then it falls off, so the more flow goes through the pump, the less the head rise will be across the pump. So we get a curve like that, and where we get that from measuring the performance of the pump. Typically we'll get that from the pump manufacturer, who has very carefully measured the performance of the pump and is guaranteeing that their pump can do this. So having been told by the manufacturer that this is what the pump can do, knowing from our calculations that this is what we think the system needs from the pump, then where these two intersect is where the system will actually operate. So we might have designed our system for this much flow and said we need this much head for this much flow, and we wound up buying a pump that had extra capacity. If we had that extra capacity, then instead of operating down here, we'll wind up operating here at a considerably higher flow rate. We may or may not want that. We may start turning one of these valves closed to slow down the flow by increasing the loss coefficient and throwing away that pump energy with extra losses that we don't need to have. Now, I mentioned before we might have cavitation problems. If the flow coming into the pump comes in at a low enough pressure that when it accelerates around the impeller inside the pump, it drops below its vapor pressure, then we may have cavitation. The fluid may boil on the blades. That's a bad thing, because when those bubbles of fluid that have boiled collapse, they send a really sharp jet down into the metal of the impeller. The result is it eats away at the impeller. So what will be specified for each pump is the net positive suction head required, the NPSH. And the NPSH required is how far above the vapor pressure you have to be in terms of the pressure at the inlet, divided by rho g, so that you can express it in height units. So if I had a pump that had a particularly high NPSH value, then I might have to move my pump down well below the inlet to make sure that the pressure was high enough at the inlet. More commonly, the NPSH will be lower, and I can actually have my pump above the water surface if I'm pumping room temperature water, which has a vapor pressure that's very low. On the other hand, if I'm pumping water that's warmer, closer to its boiling point, then I'll need that additional elevation down here to keep the inlet pressure low enough that the fluid doesn't boil inside the pump and cause me problems with performance and impeller damage.